Hey everyone. So today we're going to be talking about the applications of integration when we're trying to figure out volumes of different shapes. In order to get an idea of how to use calculus for this, we're going to go back a little bit to geometry, and figure out how did we find volumes of shapes in geometry. So let's start with a basic cylinder. If you have a cylinder that has a circular shape, if you remember, the volume for a cylinder was pi r squared times h. Now, if you're looking at a rectangular box, the volume was length times width times height, okay? Notice for both of these, the base of the cylinder right here is a circle. And then we know the area of a circle is equal to pi r squared. And then when you look at the volume, we notice how we see the area times the height. Then we go to the rectangular box and we see how with the rectangular box, the base of this box is a rectangle. And we know that the area of a rectangle is length times width. And notice how in the volume you see length times width, which is the area times height. And this isn't really a coincidence, right? This is actually a pattern that every time we have some type of base, and this base is kind of multiplied many times, h many-fold times, we get that the volume is equal to the base area multiplied by the height, right? So you see it in this formula, we see it in this formula right here. So we're going to use that, right? Moving on, we're going to say, okay, well, it seems like the general formula, anytime you have some type of base and a height, you can take the area of the base and multiply it by the height. That's going to be our generalized formula. So anytime you have a cylinder that's bounded by two planes, by a region in a plane B1, that's called the base. So that's our base down here. And you have another plane up here, B2, where these two planes, these two regions are congruent to each other. They're equal in terms of their areas. And then they are a distance, h, away from each other. If that's the case, anytime we have a cylinder that looks like this, when the base area is called A, the volume of all of the points, the volume of the entire space that's inside of this area here is really nothing more than A times H. Okay, so this is a general formula for any type of shape, any type of cylindrical shape, whether the base is a circle, rectangle, square, whatever it is, or triangle, you always just take whatever the area of the base is, multiplied by the height, that'll give you the volume. So how are we going to use this when it comes to calculus? Well, here's how we're going to use it. If you go back, you know that with calculus, we tend to use limits, right? That's what calculus introduced us to. When we were finding the area of rectangles, we used, not the area, right? When we find the area of generalized shapes that are very non-uniform, we used rectangles. We said, we don't really know how to find the area of a shape that looks like this. This shape, there's nothing in geometry that has that formula. But instead, we said, okay, we can approximate it by cutting up the space into rectangles. Why? Because rectangles are easy to calculate. We know how to find the area of a rectangle, length times width. So we said, if we cut up the area into rectangles and we find the area of each rectangle, then we can basically add up those areas and they'll give us an approximate area of the shape that we want. We also realized that the more rectangles we use, the closer we get to the actual area that we were looking at. So the closer our approximation gets to the actual area. We're going to do the exact same thing here. Here, we're going to say, we know how to find the volume of a cylinder, but we don't really know how to find the volume of a weird shape like this. So instead of getting the volume of a weird shape, what we're going to do is we're going to cut our shape, our three-dimensional shape, into pieces. And each piece, we're going to, instead of saying, this piece is kind of irregular, before we said approximate using a rectangle, here we're going to say approximate using a cylinder. So we're going to cut pieces into the shape, and we're going to say each piece, we're going to make it look like a cylinder. And if we find the volume of every cylinder, add them all up together, that gives us an approximate volume of the shape that we're getting. Okay, so notice how we're doing the exact same thing we did before. We're just going, instead of a two-dimensional version, we're going to go into a three-dimensional version. Before we cut the shape into rectangles, here we're going to cut the shape into cylinders. All right, so how are we going to do this? The way we're going to do this is we're going to say, first, take a knife. You have your three-dimensional space, right? We're going to cut the knife, take the knife and cut it into slices. So imagine like you literally have a loaf of bread that's shaped weirdly. Cut the knife into pieces that are like pieces of sliced bread. Each one of these slices over here is like a cylinder. How is this a cylinder? The way that you want to think about it is take your slice of bread and lay it flat on a counter, right? So if you're laying it flat on the counter, which part is which? The base, the face of this is going to be your base. And then the thickness of your slice is going to be the height. So the way that we're going to look at it is the base is going to be whatever the part that you see when you cut and you open up this kind of slice of bread. That's going to be our base. So this is the part where we need to find the area right here. So area is going to represent the space over here. How deep or how thick we make our slice, that's going to be our H. And so if we do that, what does this tell us? Well, if A is the area of the cross section of S that on a plane PX that's perpendicular to the x-axis, meaning A represents this area right here. And your slices are going to start from wherever the shape starts all the way to the end. So if our shape starts at A and goes all the way to B, we're going to keep making slices from A all the way to B. And we're cutting it. Remember, think about, we're cutting it every time we cut it. The rectangles, we used to cut them with the same width all the time, right? They were the same delta X was the width all the time. Here, we're going to make them all the same thickness. So which means that from here to here is delta X. From here to here is delta X. So delta X represents what? The thickness of this slice right here. Well, we said the thickness of the slice is H. That's the height of it, which means the height is going to be delta X. So now what do we have? We have two pieces. We have the area and we have the thickness, which is the height. And we know from the previous formula, we said that the volume is equal to the area times the height. So our volume is going to equal to the area times delta X. This gives us the volume of this one slice over here. Well, what are we going to do? We're going to do it for all of them. We're going to find volume 1 is going to be the area right here times delta X. The volume 2 is going to be the area times delta X. The volume 3 is going to be area times delta X. And you do this over and over and over. Once you add all of them, you end up getting the approximate volume of the entire thing. Now notice as we're doing this, when you're cutting these slices up, if I cut the slice that's in the middle, like in this first picture over here, notice how the area is pretty big, right? Because the shape itself is pretty thick in that area. But if you're getting a slice in the beginning, you notice how the area over here is going to be pretty small. And so the area will vary as you go from A to B. Some slices will have a big area, which means that cylinder is going to have a big volume. Some slices will have a small cross-sectional area, which means this is going to be a cylinder with a smaller volume. And that's what we want, right? We want the area to be different, so meaning that the volume is going to be different depending on where you're located. So for our shape, in order to find our volume, we're going to take each piece, depending on where we're at. If you're starting at the first shape, we're going to use the area at x sub 0 and multiply it by delta x. That's going to be the volume of the first shape. If you're starting at the second slice, then you say your volume is equal to the area at the second x times delta x. If you're here, you're going to say the volume is equal to the area at your third x times delta x. And every time my x is different, depends on where I'm starting. Adding all those up together will give us the Riemann sums. So as we take the slabs and approximate, add them all up together, everyone is going to have their own volumes. If we take the sum of all of them, we get the Riemann sum of the area of each slice times the delta x, which is the height. Now, what do we know from before? When we were doing area, every time we took the rectangles and added more rectangles, we increased the number of rectangles, we got closer and closer to the actual area. The same exact thing happens here. The more slices we take, the closer we'll get to the actual volume, which means that if n represents the number of slices, as n gets larger and larger, as n goes to infinity, we end up getting closer and closer to the actual volume, and eventually, as the limit of n goes to infinity, the limit of the Riemann sums ends up going to the exact volume that we want. So for us, we can say that the limit as n goes to infinity of the Riemann sum a of xi times delta x will equal to the actual volume. It's no longer an approximation like over here. It will actually equal to the volume. Now, if you guys remember from previous section, we had a way of representing the limit as of the sum, right? We said that another way of denoting the limit of the Riemann sum is using the definite integral. So the definite integral from a to b of the area multiplied by delta x, which is really another way of writing, remember, capital delta. We can write it down as a to b area times delta x. This will give us the volume that we're looking for. And that's going to be our definition for a volume, okay? As in order to use calculus to find the volumes of shapes that are irregular or not something that, we have a formula for, we're going to say if S is a solid that's bounded from A to B, starting at A, x equals A to x equals B, if the cross-sectional area of S on a plane P of X that's perpendicular to the x-axis is A of X, and the area is continuous, then the volume is really nothing more than the limit as n goes to infinity of the Riemann sum of the area times the height, which is delta x. Another way of writing that is saying the volume is equal to the integral of the area multiplied by delta x. Okay, as when we're finding the volume, some of the things to remember is that as you're going across and you're trying to find the area, every time we cut, we're always going to be cutting perpendicular to the x-axis for now. Later on, this is going to change a little bit. But for now, we're going to be cutting perpendicular to the x-axis. So your shape, when you're opening it up, you want to think about you're looking at the area as if you open this shape in half, and now you're looking at it. You're looking at the face that comes up when you open it up. As you're, for the cylinder, the cross-sectional area, A of x, is going to be constantly equal to A of x. So there's going to be a formula that we need to figure out. What is the formula for the area? Meaning that this area, even though the area is going to be changing, the formula for the area is going to be the same across. Okay. So let's go ahead and figure out how we're going to do that. For us, we are going to focus specifically on things called solids of revolution. So we're not going to think about for now anyway, we're not going to think about all different types of shapes. Specifically, we're thinking about shapes that are created in a special way. They're called solids of revolution. The way these shapes are created is that you take a graph. The graph can be anything, you just want a curve. And then you take this curve and you rotate it about a specific axis. So the shape that you're creating is going to have some type of boundary. It's going to be bounded by A, by B, so x equals A, x equals b, and the curve. And then you take this curve and you rotate it around some type of axis. Here, I'm going to rotate around the x-axis. By rotating it, you want to literally think about, you have like a windmill, right? This windmill is just kind of going around in circle around this x-axis, which means that you want to think about you're doing something like this. So what's going to happen? What's going to happen is that you're going to see a mirror image of the shape that looks like this. When we rotate a curve about a given axis to get this, to get the surface of a solid of revolution, for the purposes right now, we're doing it around the x-axis, but we can also do this around the y-axis. We can do it around any axis that we want. The curve that's the resulting shape that we get, the solid, we call this a solid of revolution. So let me show you guys a image of it. So this shape right here, we're going to take this curve. This is just a function, so the yellow represents a function. And we're going to take this function and rotate it. Now we're going to rotate around the y-axis. So you can rotate around any axis that you wish. Notice how the shape that's created looks like a circular shape, right? It's a solid shape that has, when you look at it here, if you cut this at a cross section, what happens? You end up seeing a circle. So pay attention to that. All these solids of revolution are going to be obtained by revolving some type of region, meaning there's a curve, and then you're going to take that curve and rotate it around about a line. When we're calculating the volume for a solid of revolution, we said the volume equals to the integral of a of x times d of x, which is the height from a to b. Depending on what you're revolving around, it might actually be easier to find it using the integral from c to d of ay dy. So which one are we going to be using? A of x and a of y both represent the cross-sectional area of the function of, but depending on which one you're revolving around, which your axis of revolution, we either use the area with respect to x or the area with respect to y. That depends on your axis of revolution. So let's go ahead and look at the first method. The first method I'm going to show you guys is going to be called the disk method. The disk method says whenever you want to find the area of the cross section, cut the cross section perpendicular to the axis of revolution. So in this case here, we are going to rotate the square root of x, and we're going to rotate it around the x-axis. So if I'm going to rotate around the x-axis, what does this mean? It means that my cut is going to be cut perpendicular to the axis of revolution, which means my knife is going to cut down this way. All right, so let's look at that. So first my shape is going to be rotated, and I create this solid shape, right? This has like a circular shape. And once I have that, we're going to cut in the middle. We're going to take a knife and we're going to slice in the middle and take one piece out, which is going to create our cylinder. And that's what our cylinder is going to look like. Notice how here, our cylinder, when you cut this in the middle, you're going to see a face, and the face is representing, this is the thing that we need to find the area of. Notice how the area is a circle. Just like before, in that other shape, the area was a circle. The face had a shape of a circle. So our job here, when we were trying to figure out the formula for the volume is equal to the integral from a to b of area times delta x, what's the area? Well, the area is the area of this shape over here. If you want to get the area of that shape, what's the area of a circle? Well, the area of a circle is pi r squared. That's the area. So whatever formula I need to plug in here is actually going to be the formula for the area of the shape that you're looking for. And in this case, my area is really nothing more than the radius squared times pi. Well, let's figure out a formula for that. With respect to x, the radius of this shape is going to be the distance from your axis of revolution, which in this case is the x-axis, to whatever the shape ends. Well, the shape ends where? The shape ends at the the function y equals square root of x. So the distance from the 0 point to the function, the distance is really nothing more than the square root of x, which means that my radius is equal to the square root of x. So my area is pi square root of x squared. And so up here, when I'm trying to find the area, I'm going to say the area is pi r squared times delta x from A to B. And this is going to be the general formula that we use for here. Anytime we're looking for a volume of a solid of revolution, the solid of revolution is going to create a cross-sectional area that is a square, that is a circle. And so we go back to the formula of a circle and we say, since the area of that cross-sectional region is pi r squared, finding the volume of a solid of revolution is really nothing more than taking pi r squared times delta x. So this is going to be our formula for the solid of revolution. If you're revolving around the y-axis or a vertical line, it'll be, the formula is pi r squared, but instead of using a dx, we're going to use a dy. Okay, so let's go ahead and see an example of that. An example is, if we want to determine the volume of a solid that's obtained by rotating a region that's bounded by y equals x squared, x equals to 0, and x equals to 2 in the x-axis. And we're going to rotate about the x-axis. When you're doing these, first step, you want to go ahead and draw a picture for yourself so you can have a better idea of what this solid looks like. So step number 1, I'm going to graph. For my first function, I'll draw it in black, is y equals x squared. So 0 goes to 0, 1 goes to 1, 2 goes to 4. That's my first shape. My second one is x equals 0, which means it's going to basically start here, and x equals 2, which is here, and the x-axis, which is here. So I'm looking for the region that's bounded by all of these. What's the region that's bounded by all of these? I am looking for this region right here. Okay, now I have the region. If it makes it easier for you, go ahead and outline the region, and you can erase everything else. So you can erase all the extra parts of the functions that you don't really want, because these guys are not going to actually play a role anymore. Now that I have my shape, I go to my rotation. I am rotating across the x-axis, which means I'm rotating this way. I'm basically kind of making a circular motion this way. So you're going to see a mirror image of the shape down here. And it's just going to have like more, it looks kind of like a horn. And this is the shape that we're finding the volume of. All right, now that we're doing this, we need to figure out the cross-sectional shape. And you can see how if I cross-section, we're always cross-sectioning for the disk method perpendicular to the axis of revolution, which means we're cutting this way. So if you're cutting this way, notice how you have a circular shape. And so when we're finding for number 2, we put our formula, volume is equal to the integral from A to B of pi r squared dx or dy. Okay, so what do? First step, figure out, am I dealing with a dx or a dy? That depends on, are you rotating around the horizontal line or vertical line? If you're rotating around the horizontal line, like the x-axis, then you're going to be a dx. Okay. Second step, we need to figure out what is the bound. What are the A? What's the B? Bounds represent where is the shape, the original shape. Where is the shape starting? Where is the shape ending? Well, because the shape started here at 0, and the shape stopped here at 2, because they told us go from x equals 0 to x equals 2, A and B is equal to 0 and 2. Then we need to figure out, so this is my A, B, and C. I need to figure out what's the radius. So notice how I'm looking at the formula and I'm trying to figure out what are the pieces that I need. I need an A, a B, and a radius, and a dx or dy. So to figure out my radius, you go and you say, okay, what's the distance from the axis of rotation? You're always starting at the axis of rotation because that's the middle of the circle right here, right? So since that's the middle, we say, what's the distance from the axis of rotation to wherever the circle stops? Well, the circle stops at the function, stopping at y equals x squared. So the distance from 0 to x squared is x squared. So my radius is equal to the function, which is x squared. Now I have all the pieces. Once you have all the pieces, the last step, you plug it into the formula. You say volume equals to pi integral from 0 to 2 of the radius, which is x squared, squared dx. That's the same thing as saying pi integral from 0 to 2 of x to the 4th dx. And then we go and say, okay, this is pi, take the integral as we usually do. Notice how I simplified first, and then I'm going to take the integral, which gives me, plug it in. We're going to plug in the bounds now. We say this is going to be equal to 5. So it's x to the 5, so 32 over 5 minus 0 over 5. And that gives me 32 pi over 5. So in this case, the volume of the solid revolution that was created by this region is 32 pi over 5, whatever the units are. All right, let's look at another example. For another example, we're going to go ahead and take another shape, which is bounded by square root of x, x equals 1, x equals 4, and y equals 0, and rotate that about the x-axis. So same thing. First step, you want to draw a picture for yourself. For my first bound, I have square root of x, which means starts the 0 goes to 0, 1 goes to 1, 4 goes to 2. This is my first shape. My second is x equals 1. X equals 1 is right here. And then x equals 4, that's right here. And y equals 0, that's over here. So I need the shape that's bounded, the region that's bounded by all rows, which means that it's really this part over here. Now, as usual, like I said, you can go ahead and basically draw kind of like a boundary for that. That way, if you want, delete everything else. So I'm going to go ahead and just draw a boundary. Say, okay, this is the area that I want. And I'm going to delete everybody else just to erase all the other parts that I don't need. I need this part and this. And that's the shape that I'm looking for. I'm going to write down, this is just to remind myself, this is square root of x. This is x equals to 4. This is x equals 1. Right now, in order to rotate, I'm rotating about the x-axis, which means that I'm going around this way. So I should see an image, a mirror image down here at the bottom. So it'll look like this. And it's going to rotate like that. That's my shape that I'm finding. The volume, which I'm finding the volume. Right now, that's step number 1. Step number 2, because we're using the disk method, we're going to say the volume equals to the integral of pi r squared, that's the area, from a to b times the height, which is delta x. So I have a couple of things to find. Number 1, I have to figure out, am I dealing with a dx or dy? I already put it here, but we're finding it. Second, you need to figure out what are your bounds. What's your A? What's your B? Meaning what's the leftmost, what's the rightmost bounds of this region. And then step number 3, we need to find the radius. Once we have all those, we're going to plug it into the formula and do the calculation. So the first part, am I dealing with a delta x or delta y? It depends on your axis of revolution. Because my axis of revolution is horizontal, I am dealing with a delta x. So that tells me up here, I'm just dealing with delta x. Second, my bounds are representing the bounds of whatever variable you're using. So if you're a delta x, your bounds are the bounds for x. So you're asking yourself, from the left to the right, what's the farthest to the left that the region goes to? So this original green region, the farthest to the left it goes to, starting at x equals 1 right here, which means my a is equal to 1. What's the farthest to the right that the region goes to? It goes to x equals 4, which means my b equals 4. Last step is the radius. When we're doing the radius, remember we are cutting perpendicular to the axis of revolution. So if your axis of revolution is horizontal, you're cutting up and down. So you're gonna go like this, you're cutting this way, and when you slice it, you should see a circle where this part right here is your radius. All right, so my radius is a distance from the x-axis to the function up here. Well, what is that function? Well, the function was square root of x, which means my radius is just the distance from 0 to square root of x, so it's square root of x. Now that I have all my pieces, I plug them in and I say, okay, the volume equals to pi times the integral from 1 to 4 of square root of x squared dx. That is the same as pi integral from 1 to 4 of x dx, which is x squared over 2. And now we plug in the bounds. Plugging in the bounds, I will get pi, and I just leave pi in the outside. I don't do anything with it until the end. It's going to give me pi, plug in the 4 first. That's going to give me 16 over 2 minus 1 over 2. And that will give me pi times 15 over 2. So 15 pi over 2 is my volume. That's still what I'm looking. Right. Let's try another one. So remember I told you, you can technically rotate everything with respect to a horizontal axis or a vertical axis, right? So you can rotate around either one. Let's try one where we're rotating around the y-axis. We're going to do the exact same one we did earlier, and I want you to see how the new shape that's created is going to be different than the original shape the way we were rotating around the x-axis. So the volumes are not going to be the same, right? So don't assume just because you're dealing with the same region that the volume will be the same. The volume will change based on the axis of revolution. So the first step, same 3 steps. Step number 1, we are going to graph our function. So here we have our first one is the first function is going to be y equals x squared. So I'm going to go ahead and graph that. So 0, 1, and 4. This is my region. My second was x equals 0. That is this over here. And this is actually a typo. We're going to say y equals to 2. So we're going to do this one over here. This line. Y equals to 2 instead of x equals to 2. All right. Now, if our shape is bounded by y equals x squared, x equals 0, y equals to 2, don't worry about this part. This is a little typo. And it's being rotated around the y-axis. What's the shape? The shape that we have over here is going to be this shape over here. So it's a little different than the one earlier. We'll do the one earlier a little later, but it's a little different because before we were taking the shape that's on this side. Now I'm actually taking the shape that is on the left side, which is this one. Now I'm going to go ahead and bound it like before, draw a little bounds for boundary, and then I'm just going to delete everything else that I do not need. So to remind myself, this is y equals x squared. This is y equals to 2. And this is y equals to 0, or x equals to 0. Right, now we're rotating across the y-axis, which means we're rotating this way. So if we're rotating this way, we should see a mirror image of this on this side. And it's going to look like this. The shape is this way now. Now remember, with the disk method, we always cut perpendicular to the axis of revolution. So if my axis of revolution is vertical, we're going to cut this way. Our knife is going to come horizontally. So for number 2, for number 2 here, we're going to take the cut this way. And we have to find a couple of things, right? Looking at the formula, we have pi AB radius squared dx or dy. So what's the first step? The first step is figuring out, are we dealing with a dx or dy? Well, remember, it depends on your axis of revolution. If you rotate it on the vertical axis, then you're going to be using a dy. So for us here, we are using a dy. This is important to do first. Why? Because now we're trying to find the bounds of A and B. Well, the bound represents how far left or right, or how far up and down. How do you know which one? It depends on what's the variable. If you're dealing with a dx, then the bounds are representing what are the bounds for x. That means you're looking at how far to the left, how far to the right. If you're dealing with a dy, then the bounds are the bounds for y, which means you're talking about how far down, how far up, right? So in this case here, because we're dealing with a dy, we're really asking, what's the lowest y that this function goes to? What's the highest y this function is going to go to? Function means I'm talking about the region. The region that's being rotated, this black area over here, what's the lowest it goes to? Well, since this one is starting with 0, our A is 0, and it's stopping with 2, that means our B is 2. The last part we need to find is the radius. So our radius is representing the distance from the axis of revolution to the outer part of the region. Well, this is our rigid circle right here. The axis of revolution is at y, is at x equals to 0. And this thing is stopping where? It's stopping at the function, which means our radius is from the 0 to the function. Now you might be tempted to say, okay, well that means it's x squared. But remember, inside of our integral in this case, we're going to have an integral where we have a delta y, which means what? It means that our formula needs to have inside of it a y. It can't have an x. So even though our radius goes from 0 to the function, we can't write the function as x squared, because then you'll have a y and an x squared. We can't do that. These two variables have to agree. So how do we fix that? The way that we fix it is we say, okay, our radius is going to go to y equals x squared, but another way of writing that is x equals square root of y. So our radius is actually going to be square root of y. And that's what we put over here. We say square root of y squared from 0 to 2, and that's going to give us pi integral from 0 to 2 of y dy, which is equal to y squared over 2 from 0 to 2 times pi. That's going to give us pi times 4 over 2 minus 0 over 2, which is equal to 2 pi. That's our volume. All right, so this method is going to be used to find the volume of axis of revolution. In the next one, we're going to look at how to find the volume using something called the washer method.